This is section 2 of the CVP basic camera course. So now we're going to talk about concepts of the digital camera, beginning with analog and digital concepts in imaging. So charges from the pixels must be converted first to a voltage, and this is done with a capacitor circuit, or more accurately, an analog to digital converter. The voltage levels must be measured and converted to a number, done with an analog to digital converter, and along the way the gain and offset can be adjusted before the conversion. So the analog digital converter will represent the voltage levels, or the grayscale level of the camera, as binary numbers. As humans, we tend to use 10-bit math, and we think in decimal, and we count 0, 1, 2, 3, 4. But computers and digital devices like cameras can't think like this, and it would take more lines. Computers think in binary, which means a number is represented only as a 0 or 1, and then they count in binary, or as in mathematically, this is represented as base 2 math. So in binary, then the digits are rolling. You can imagine this is like an odometer in your car, but with just a 0 and 1 on the odometer. So it rolls from 0 to 1. When the 1 rolls, it rolls back to 0, but it rolls the next digit to 1, which stays at 1 until this one saturates again. And when they both go to 1, they both go to 0, and the next digit goes to 1. So just think it like your odometer, but there's nothing but a 0 and a 1 on here, and we count in binary. When the camera then makes a digital signal, it just simply has to make a bit higher or low and string the binary number out in a single serial stream. So why is this important for imaging? Then what happens is we tend to think of the grayscale values in the camera. The camera is converting light into a value, and the more bits we have in the value, then the more grayscales we can have, and the more accurately we can measure that light. So the depth of the camera is then called the bit depth, and that's how many bits per pixel are being represented in the image. So if we start at the bottom, this is what we would call a 1-bit image. That means every pixel only has 1 bit represented in it, which can only be a 0 or a 1, or black and white. So there's only those two values available. So if I looked at a shaded area, then I see only black and white. If we increase to 4 bits per image, that means now instead of using 1, I have 4 digital numbers, and 2 to the 4th power means I have 16 gray values. Then I can have 16 values as I go from dark to light. A little more accurately represented, but you see it's still somewhat cartoony. An 8-bit image, which is the most common math done in machine vision, 2 to the 8th power is then 256 values, and I have 256 gray values, and you can see that I have a fairly smooth transition from white to black. We've left this blown up and a little pixelated to make the point for you, but essentially I have enough values to make a transition that is smooth to your eyes. So you would say, well, why don't I just want more, and why don't I have 12, 14, 20 bits just all the time? Well, there's some high bit considerations. With more bits, you get more accurate measurements of light. But with more bits, you also have more data to transfer, process, and store. Since the data from the image that's going across my interface method, and we'll talk about interfaces near the end here, if I transmit 12-bit data instead of 8 bits per pixel, then I have 50% more data per pixel. And when we talk about megapixel cameras, 1 megapixel, 2, 4, 8, all the way up to 20 and 30 megapixels nowadays at a high frame rate, this becomes a lot of data. So you want to manage how your bit depth for what you need with the application to get enough bit depth and resolution, but yet manage your data and keep it minimal to manage the data transfer and not create a lot of extra work in a PC for properties you don't necessarily need. The other consideration is the accuracy of the image. With more bits, if I have a 10 or a 12-bit image, then I have 1,000 or 4,000 grayscales per image, which means I can more accurately sample the light, but it also means I more accurately sample the noise. It doesn't necessarily mean there's more noise, but it means that I can see the noise in those last bits. This is good in some applications. Some high-end medical and others actually use those bits and that noise to calculate and do some noise analysis and remove noise from sequence of images. But in general, over-digitizing and digitizing the noise portion of the camera is not useful and creates just extra data that's not useful bits. So we see this a lot too. It doesn't make sense to put a 12-bit output on a camera that uses a small pixel CMOS imager. We talked about the small pixels in section 1. And if you only have a 4,000 electron pixel, it doesn't make sense to have 4,000 grayscales, because in the charge conversion, you're not going to see a single photon in the well. So the signal noise ratio of a 4,000 pixel small electron imager is very small. In fact, it's probably only 30 or 40 decibels. To get 8 bits, you need at least 48 dB of dynamic range or signal noise ratio. And to get 12 bits, you need 62 decibels. So it does not make sense to put a high bit depth, 62 dB type of output on an imager that only can make 30 or 40 dB. So what are the benefits of digital cameras? Why do we see the whole world going from analog to digital, whether it be consumer camcorders, whether it be machine vision cameras? What's going on here? So in the early days, we talked about, in section 1, we talked about the TV formats. Everything camera-wise was analog in the early days, because I expected to go home and plug it in a TV or plug it into my VCR and record it. It was a standard format, it was transferable, and everything worked together, and the whole world was analog. But as we saw, as imagers became higher resolution, as we became progressive scan and not interlace scanning, we left some of the standard formats. And in fact, in machine vision, we want non-standard formats. So one of the drivers here is just getting our arms back around these non-standard formats in a way we can handle. But there are actually advantages to digital cameras as well that you don't see in the analog camera. They start with the configurability. Analog cameras tended to also be configurable by switches. As the world moved on, we do have RS-232. Some high-end analog cameras had serial control by a PC, but by and large, analog cameras went back to the TV days and probably have buttons and switches on them. Digital cameras, because they're digital by nature, they came along after the fact in the product development, already have a little brain in there to drive it anyway, so that brain tends to be digital and we can talk directly to it. And not only can we talk directly to it, in a lot of cases there's extra processing and there's features we can do inside the camera. So here you go. With an analog camera, we tended to have, this is a representation of the analog signal. Here's the sync. Here's the grayscale values of a horizontal line of the image. And it would go into a PC for machine vision. In the consumer world, you would connect it to your TV or VCR, but of course, we're concerned about the machine vision world. And in a few applications, you might be monitoring or something, but in most cases, users then have to convert it to digital to get it in the PC to actually do some analysis of the image and create an output or an action that we expect in machine vision. So by doing this, this actually meant we took the nice flexible analog circuit or output from the camera and ran it into a digitizer, but then when we have that, that can create some problems. Pixel jitter between the two devices. This has to sample precisely at the clock frequency of this. It uses a phase lock loop to lock onto it, but there's always a little bit of jitter. Noise and EMI suppression go hand in hand, and an analog signal, by the standard, this is 1 volt peak-to-peak signal with approximately 270 millivolts of sync. That means that only about 700 millivolts, just over 700 millivolts, represents the entire analog portion of the signal. As we saw again in section 1, the pixel intensity is being converted to an analog blip that is being represented here somewhere on the horizontal line. So what that means is, hey, I'm running down a single cable with this analog signal, and I've only got 700 millivolts representing my full scale, my pixel, and only 1 millivolt representing the bottom end of that pixel. Actually, in an analog signal, there's a 50 millivolt offset to compensate some of this. But essentially, I have the entire signal at 700 millivolts. That means if I pick up as little as like 10 millivolts coming down my cable, those 10 millivolts are a substantial portion of that 700 millivolt signal, and that's where you see noise or interference. So if you've ever seen TV and you got a bad signal off your antenna, or if someone started a motor or something noisy around it, you see snow on the screen, that's because it's making spikes in here, and those spikes are being interpreted by the receiving device as a bright pixel or a dark pixel if it's a dive, and that noise is very inherent on here. A digital camera makes a chain of zeros and ones, as we described in the binary counting, and transmits them over the interface. This is inherently more immune to noise because the noise must upset these two scale levels, and either, depending on the method of transfer, either these are a higher voltage, it has to be several volts before it toggles from a 0 to a 1, or it may be current driven where the voltage level is low, but it takes a lot of current. So even if there's noise, it makes a little bit of voltage online, it can't really build any charge because there's no current behind that noise that's being picked up. So therefore, I'm transmitting zeros and ones. The receiver only has to tell whether the line toggled way up here to a 1 or way down here to a 0 to get it right. And if there's noise, it has to be so great that it upsets it, and probably it's not the camera's probably not the only thing that's upset if you have that much noise in your environment. So inherently, digital is more immune to noise, and correspondingly, it's more immune to EMI and other noise sources. So this is very important in the factory settings. As a camera manufacturer, I've definitely experienced cases where people have done installations, they run cables too close to 100 horsepower electric motors is the thing that comes to mind. And in my mind, I saw a case actually in an automotive plant where they literally had run a gigabit Ethernet cable over a 100 horsepower electric motor and were inducing currents in there. So digital is not immune entirely, but it's more immune than analog. So when we talk about digital camera benefits versus analog, as I said, analog has the standard formats, AIA, NTSC in the United States, CCR, PAL in Europe, but these are standard formats. I can plug anything together, it works, but it is, in fact, analog and has the disadvantages we talked about, including interlace scanning. Whereas digital, we have different formats. We might have different resolutions, VGA, SVGA, XVGA, or as we leave these and go, we see resolutions all the way up through about 30 megapixels nowadays. The frame rate might be different as well, not only the resolution, the aspect ratio, whether it's a 1:1, a 4:3, wide HD TV, which happens to be 16:9 aspect ratio. Those are all varying things that we have to deal with on the capture end, but in the digital world, we just deal with those in the interface standard. So we make a standard that takes care of all these, and in most cases, and we'll talk about the standards, either the format is predefined or it's flexible, and the camera says, I have this many pixels horizontally, I have this many vertically, and the digital device configures itself. But the point being, in the digital world, we have the communication and the wherewithal and the tools that we can set up for these non-standard formats, whereas in the analog world and your VCR and other things, there's just no way. Either it fits that format or it doesn't, and if it doesn't, then you got to go get an analog capture card and configure it. So digital allows us the chance to standardize the output and make plug-and-play type interfaces. So analog does have more than one format. I've described mostly what we would call a composite format, which is the single cable that you're accustomed to, either a coaxial cable bringing the raw signal from the antenna, or the RCA type that goes on the front of the VCR that contains only the analog signal. But in analog, there are other cases. There's SVHS, also called YC video, and this means it breaks the analog signal into two components, one for intensity, one for the chroma. or RGB, which means there's now 3 or 4 cables. There's 3 if it's RGB and there's sync on the green. There's 4 if the sync is brought separately in RGB. But what that means is there's a separate channel for red, green, and blue, and that channel is only intensity. So RGB is actually the highest level analog format because the color components are separated each to their component plane, and that gives a chance to have less crosstalk in between the colors. And composite, because there's a chroma burst for the entire signal that's 4 times the speed of the rest of the information, then that means there's a little jitter and crosstalk among those colors. And SVHS or YC, where there's 2 cables, or somewhere in between. But in digital now, there's no crosstalk because we represent it as a number. Each pixel goes out discretely as a number. But there are different formats. There are ways I can tell, I have to tell the host that this pixel I just sent you was an RGB pixel and has everything in one pixel, red, a green, and a blue. It's a 24-bit component with 8 bits of each. It tells it that I'm a YUV pixel, so I'm not going to go into coding here, but there's coding that says this is how I encode a digital standard YUV 422. Might be a monochrome, just saying there's a single 8-bit or a single 16-bit value for this pixel I sent you. Or it might be raw bare, which means I'm just sending you the raw pixel. It's a red pixel and it has this 8 or 10-bit value. And you take that value, and when I tell you about all the red, green, and blue, you use your own host-based interpolation to get your color out of that raw data. But the point is the digital standard has to know what type of pixel, not just the pixel and the value coming at it. Digital cameras can also provide advanced features. Again, because they are being driven essentially by a small microprocessor inside, whether it's physically a microprocessor or it's another type of logic device like an FPGA or an ASIC, there's a device inside driving all the digital electronics, clocking the imager, and correspondingly we can talk to that device and we can build features in. Most notably, some of the basic features that are most commonly used are things like test patterns. So in a digital system, if I plug it together, I'm not getting an image, I'm not sure what's going on, I can go turn the test pattern on in the camera, and I should see it on the other end. And if I don't, I can start troubleshooting about where my signal went. But it also includes things like timestamps, frame counters, settings on my I/O ports if I have some input-output connected to the camera, things like error checking. I can check not only I sent it across, but at the end of receiving a frame, I can have a checksum or some kind of error checking and check back and make sure that I didn't introduce errors in the middle of that frame or miss a pixel. All types of things come with digital benefits. So digital cameras can do onboard processing as well. Again, because there's a brain there, often to get all the I/O and the stuff I need to make a camera, I had to use a bigger processor inside that camera in order to get all the structure to interface it to the outside world, but it actually had processing left over inside. And then what you see is manufacturers trying to make unique things to separate themselves from other manufacturers and attack various applications. With the features we can then build into these smart digital devices. So in this case you're seeing here, this is actually a 2 CCD camera where I have 2 CCDs aligned per pixel on a prism. I'm getting 2 simultaneous images, but one image is being set at a high gain and slower exposure so I can see inside the car and see the faces, while the other image is out here where I can see the headlights and presumably the license plate if I wanted. But it's too dark to see inside the car. And with the range of a single sensor, I couldn't see both. If I turn it up to see the faces, then I'm washed out around the headlights, and if I were trying to read that license plate, wouldn't see it. Yet if I turn it down to see those features, I can't see the faces at all. This camera then, because it has a digital brain and processor, is able to take the 2 images, fuse them into one high dynamic range image where I can see everything inside the lights, the glints on the paint, but also inside the car. And because it's done in the camera, it's just served up to the user as a high dynamic range. All of a sudden the user has a camera that attacks an application that was previously a problem for a single camera. In the analog realm, we simply couldn't do this kind of processing. So this is, again, an example of what's going on in that camera, looking at a light bulb. Again, if we want to see the filament, we have to use a very fast shutter, very low gain to see the filament without it glowing. But if I need to read the text, there's no chance in there. The camera can line the two on the prism, do it, and read it all out to one image of the user where you can see everything he needs, including the glass around the light bulb. You can see in fine detail, print, and everything. So this, again, is made possible because we have a smart processor in the middle, and I can do image processing and actual fusion, feed it through a memory circuit, and now the rest of this would be typical output for the camera. A physical interface and a format, in this case, gigabit Ethernet for vision. Okay, so now we want to talk about image quality basics. Those include temporal noise. Temporal noise is anything besides light that can change its pixel's value over time. Things like temperature, random noise, thermal noise. As the sensor, if we take a camera and start getting it hot out in the sun, we'll see the noise level come up. This shows up like snow on a TV screen. That is temporal noise. The pixel's value is changing, and it's not steady. It's changing with time, temperature, or something. Spatial noise, then, is fixed, often called fixed pattern noise. It's fixed. It's still a noise source. This pixel value is not right by some value, but it's constant. That value doesn't change. So there's still an error there, but we can correct things like pattern noise out. So this is where CMOS sensors typically have things called fixed pattern noise corrections. They also have some more advanced corrections sometimes, and what they're going for is a spatial noise where they know that there's noise that's not real, that they have to get out of the image, get a higher quality image, but yet they know their sensor and they know the parameters around them, and they can apply a correction because it's fixed. Temporal noise cannot be mathematically corrected out. Might be averaged out over a number of frames or some other corrections, but in a single frame you cannot mathematically correct temporal noise because there's a random nature to it. So some sources of temporal noise. Shot noise or photon noise. A lot of people don't recognize, you hear this and see this, but they don't recognize that this is due to the nature of light. Shot noise has nothing to do with the camera. What it amounts to is light is a wave, as we described at the very beginning, and waves can cancel out. So if I have a bunch of rays coming at my camera at a certain light level, then a certain number of those rays before they get to the camera get out of phase of each other and they actually cancel each other out, and then it doesn't register on the camera. So in bright light, if I have a large number, if a pixel was going to be filled up with 40,000 electrons and I have 40,000 rays of light coming at me, you don't see this random cancellation. You're not very affected by shot noise. But as people turn the gains up and I get in a low light situation, and maybe I had a 40,000 electron well, but I'm only going to use 5,000 or 6,000 electrons of that well and turn the gain up at the end to get my image brightness back, then all of a sudden at low photon counts, you can see that some of them canceled. And again, you see this as a random noise source because in this pixel, a few canceled, and that one they didn't cancel. In fact, maybe they added and got brighter. So you see random variation from pixel to pixel that is just based on the nature of light. And again, that's called shot or photon noise. Dark current noise then varies by sensor. In the example here, it says every 8C, the dark current noise doubles. That's an average value. It varies by sensor, though it's usually in that range. And what's happening is the sensor is collecting those photons, converting them to a voltage or a current for the device, but no matter whether it's a CCD or a CMOS imager, it needs to collect those lights and read out a value for them. But during the time that it's holding the charge, getting ready to read the value out, there's always some what we call leakage current leaking in here, and that's called dark current noise, and that's because there shouldn't be any. Even if I cap, it's called dark current because even if I cap the camera and output a black image, we can measure the electrons that are flowing into the well. And it's essentially the fact that my bucket is not really a bucket. It's a little bit leaky. You can imagine maybe a well built with bricks or something where there's a little bit of light in the side. So if I hold the light for a long time, say I do a 4-second integration to get a real low light image in a scientific type application, you can actually measure those photons creeping into the well, or those electrons that were never really were photons, but they creep in the well anyway and get measured, and that's called dark current noise. That creates a fixed offset to the camera, but again, because it varies from every pixel, it's still a temporal noise source because it's not perfectly uniform from pixel to pixel. Then there's also quantization noise, and that's errors coming from the A to D conversion process. So whether it's a CMOS or an analog, whether it's a CCD or a CMOS imager, there's still an analog to digital converter somewhere. In the CMOS imager, the analog to digital conversion is taking place on the chip, whereas in a CCD camera, the charge is being read out of the chip and it's taking place inside the camera. But both have an A to D converter, and an A to D converter always has a little bit of what we call quantization noise, and that's where it's being affected by some of these thermal effects as well, causing a little bit of noise. Tip, use a better A to D converter to get less quantization noise. This is fundamentally important because, as I just told you, in a CMOS camera, the A to D converter is built on the chip. Not only that, there's massively parallel ones on the chip to read out all these pixels, which is fundamentally why they're faster. However, by the nature of that, they have to keep the structure very simple and very small to fit at the pixel level or at the column level, and therefore the on-chip A to D converters on a CMOS imager are nowhere near the par of a off-chip discrete A to D converter we can build in a in a CCD camera. Plus, in a CCD camera, then there's only one stream running through that one A to D converter, so there's no variation from A to D converters. So quantization noise is a big difference between CCD and CMOS cameras. This is also why CMOS cameras tend to be a little noisier than CCDs. So this is exaggerated here. This is obviously high gain. But this is showing spatial noise off a CMOS imager, and what you literally see, there's a little compression adding to this, but what you literally see is all these vertical stripes are column noise from the column A to Ds and the variations I just talked about in those converters. And you can see that in there, and that's the primary noise source. There is some effect to, I don't know that bad sensor design is the right word there, but there's a sensor design effect to get more and less noise. And depending on the level of sensor you buy, certainly CMOS cameras can be cheaper, and a less expensive imager you would expect more pattern noise and fewer refinements, whereas in the higher quality CMOS imagers that you see nowadays in machine vision, you can expect a better image even if there's still pattern noise in the background. There are also trade-offs in this, so it's not always bad design versus what I wanted. For example, we were talking about global shutter. If I install a global shutter in a CMOS imager, that means I had to add an extra transistor to that imager, because unlike the CCD, there was no ground plane, but that transistor now takes up space on the imager pixel surface area, which means it has a smaller photosensitive area. So there's always trade-offs, and some of which can result in spatial noise. So I've mentioned a couple times the signal-to-noise ratio. The ratio of good signal noise is the ratio of good signal caused by light to the unwanted noise, the most important measurement of image quality for digital cameras. So again, we described in section 1 about the well capacity and having more electrons in the well. The blue electrons in this is simulating the well and the readout structure. The blue electrons are the good signal I want. This is light that's coming in, it's registering in the well. The red ones are bad ones. Some of these are random and come in from just thermal fluctuations. Some of them are still random, but they came from dark current leakage. So 3 or 4 of these might have been leakage during the readout period. The rest might be random noise. A few might be external noise sources. But whatever it is, there's some noise that wasn't light, and that can be divided, or the good noise can be divided by that and give you a signal to noise ratio. So the higher the signal to noise ratio you have, the better signal you have from the camera, the better we can digitize it and create more grayscale values and create better cameras for you. So this also affects sensitivity. Good camera designs require less light to overcome the noise factor. So if you have a bad camera design, high noise, you can't have good sensitivity, because sensitivity means I could measure only 1 or 2 photons in there. If I have a whole bunch of photons of noise, then it's harder to measure those few. So this comes back to camera design. So dynamic range then is the range from the brightest pixels the camera can measure to the darkest pixels the camera can measure. So again, I'm coming back to the light bulb example that I gave earlier, but it also serves us in this case as well, because what we can see is, again, the dynamic range of the imager is the ability to measure between a certain average black level and how far then, still measuring that black level, it can measure in the white direction. And we can see the camera cannot measure everything to see the glass and the filament, but still read text. And if we turn it up, you can read the text, but you can't see this. So we can fuse the images and create a higher dynamic range image. But the point being is that any single CCD camera still has a dynamic range associated to it. The dynamic range is very closely tied to the signal-to-noise ratio. And generally, they don't exceed each other by too far. I'm not going to discuss the actual measurement method, but they are related. So this again is showing the signal-to-noise ratio and how this affects the camera's output. So this is the point at which the camera has no photons in the well, or the black level of the camera, so the output is driven to 0. Doesn't mean cameras are not necessarily single photon devices. So it doesn't mean there might not be light hitting here, but it means this is the minimum light that this camera can detect. And this camera is set in more or less a linear mode. So as the light doubles, the output doubles, and I have some output. And this is the saturation. This is the point at which the well is full. So at this point, more photons may continue to hit, but the well can't hold anymore, so I can't read out anymore. The distance between the minimum and the maximum point is then the dynamic range. As we go low in the dynamic range or the signal-to-noise ratio, there's a point where I'm not getting any signal out of the camera. It's a very small signal. The noise floor is fixed in the camera, so for given noise, small signal-to-noise ratio is very low down here. As I have more light, then I'm getting more signal in that well. The noise level is constant. The signal-to-noise ratio is very high at the end of the curve. If available from the manufacturer, then you can get signal-to-noise ratio measurements. Typically, this is only good from a manufacturer. You're dependent on the test conditions, so it's not usually good to compare one manufacturer's curve to another's and say, oh, all things were equal here. But if you can get them, either in absolute terms where you could consider one camera to another, or for several cameras from a manufacturer, you can tell things about the camera then. A camera that's good in low light is not always the best in bright light. So you want to consider, what is the dynamic range? Am I using this camera at one point as machine vision? I always have fixed lighting, therefore I can count on this point. Or it's still maybe machine vision, but maybe it's on an autonomous robot that's driving around outside or something, so the light is changing and I'm concerned about the entire range. You want to consider that when you're buying cameras. So again, you can tell each of these cameras has a different point where it drives into the light. This is coming down to 1 lux, this is 100 lux. And the things with the highest dynamic range are usually the things with the poorest sensitivity, because if I have good sensitivity and I have high gain, that means unless I have a really big well, my well is saturated faster. So typically these things are a little bit at odds with each other, and you want to pay attention to the cameras, where the data is available anyway, and where you're going to use them. This is also a point where we want to mention the EMVA 1288 standard. This is an industrial standard for measuring the image quality of digital cameras. To date, this is the only industry standard that's available that really is applicable to compare one camera to another. There are some standards that have been out there that measure, let's say, light sensitivity, but they don't necessarily take noise into account. And of course, noise can be traded for sensitivity. If I have half the noise in a camera, I can then double the gain to get the same noise as another camera and have twice the sensitivity. So noise is a factor in sensitivity. EMVA 1288 is one of the few standards out there that takes everything, the sensitivity, the noise level, everything in the camera in, and gives you some metrics based on that. Is testing using a known set of conditions, light, lenses, and targets and stuff, so manufacturers can't fool it by cheating on the lens or some of the other parameters. Again, there's other specs out there, or the manufacturers always put signal and noise ratio on the back of a data sheet, but that signal and noise ratio you read on a camera data sheet, unless it's an EMVA 1288, is actually meaningless for comparing one camera to another, because one set of test conditions wasn't exactly equal to the other, and even when they kind of give you the basics and it would look equal, sometimes it's still not apples and apples, so comparing in the background. So EMVA 1288, again, standardizes all this in a way that there's no fudge factor, and that you can compare one camera to another. It also, to get away from variation, results from multiple cameras must be published to show the level of consistency. So same thing in the security market and low-end cameras, we see some of the highest standards that are out there because they've tested a gold camera, but the average value of a batch might not match that gold camera standard. In the EMVA testing, they have to publish a batch of cameras and look at the averages of those cameras so that you can know how manufacturing variations are affecting that camera's response in the standard, and use that to your benefit. And again, it allows customers to compare apples to apples, one camera to another, and they can be consistently sure. This is very good. My only caveat about the standard is it takes everything into account, all the noise sources, both spatial and temporal, camera sensitivities and everything. Some applications care less about things like maybe they're more concerned about the temporal noise than the spatial noise, even though the spatial noise is being held against the camera in this. So in some cases, in some very narrow cases, you may want to read in between the lines and not just say, well, these cameras are equal because they're rated, but how were they equal and what was this one good at? But again, the advantage of the 1288, if you have a full test report on the cameras, is you can see all the parameters and you have the data to make those judgments. So the last thing I'm going to talk real briefly on is what are some of the basic camera controls. And I want to emphasize the word basic. We're going to talk just about gain, exposure, and shutter and things like that. If we open a digital camera today, there's probably 50 different user parameters in there, and a lot of things that customers can control. There's a lot of special features like I've shown that manufacturers build into. We're not going to talk to that level today. We're going to talk, this is the basic course, and we're going to talk about the basics affecting the image that are most usable to the user setting up for the first time here. So the first thing we want to talk about is gain. And most people understand this concept. Gain is akin to the volume control on your stereo. So the camera is getting some light for some conditions. It's outputting. If the image is too dark, you simply turn the gain up. Just like in the stereo, if it's too quiet, I'm going to turn the volume up. But the gain is simply an amplifier. So it's amplifying the video signal, but it's also amplifying the noise and everything. It's just like in the stereo, if you turn it up way loud and the song ends, you can hear the static in between songs. The same is true in the camera. As I turn it to high gain, I'm going to see that fixed noise. And this comes back to what we've been saying all along about the signal-noise ratio and the well output. So if we look at the output signal of the sensor in percent, and then we're going to look at the output value of the camera either in grayscales or we could call it percent as well. But what's basically happening is in a low light situation, I'm only filling that well up 25% of what it would be in a bright light situation. So in sunlight, I get enough photons that 40,000 electron well is completely full, and then I can run a minimum amount of gain, 0 dB of gain, and get a full output out of that and see my image. Great imaging. But truth is, very seldom are we in those cases. So often in machine vision, we want high-speed electronic shutters to freeze the motion, but that also means we blocked out light. So if I take a 1/10,000th shutter and freeze the motion, like I showed in that motorcycle picture earlier, then that also means I only collected light for 1/10,000th of a second, and in 1/10,000th of a second, probably 40,000 electrons didn't register in my pixel well. So that means, hey, I used a high shutter, now I only got 10,000 electrons in my 40,000 well, so I'm only 25% of that well, so how am I going to get my full output back? I'm going to apply 12 dB of gain and multiply that up and get a full scale count out. But again, that means I multiplied the noise up as well. So I want to pay attention to the gain. One of the principles in imaging is that if I can keep the gain low but apply more light in any kind of way, if I can live with a longer shutter speed, or better yet, if I can just use twice as much light, then I'm going to get a better quality image. And always it's better to increase the light, open the f-stop in the lens, or apply twice as many lights than it is to apply gain. However, there's downfalls to some of those. It's not always possible either. It's not practical to apply more light. You need a shutter to freeze it. It's not practical to limit the shutter. You're going to turn the gain up in the camera at some point and recognize it affects your signal to noise ratio. Notice it also affects my dynamic range. Again, the dynamic range is the ratio between the light that's black and how much light it takes to saturate the imager. So at full well capacity, I have a very high dynamic range if I measure these ratios. But if I've only used 1/4 of the well and used 4 times the gain, then my curve is steep and the light range, the light it takes to saturate is now only 1/4. So the dynamic range is cut by a factor of 4 as well, since the noise floor didn't necessarily move in the camera. So it's important to recognize that, because a lot of our customers don't recognize that turning up the gain affects the dynamic range of the camera. They might think in terms of, well, I knew the signal to noise ratio fell, but they didn't necessarily understand the dynamic range fell. So for gain, then increasing gain will increase the visibility of both signal and noise. Does not increase image quality, in fact decreases it because it amplified the noise. Use only as a last resort, as I described. Turn up the light, open the f-stop, anything you can do if you can do it. And gain may be limited at higher bit depths. So if I have a high bit depth camera, it doesn't make sense to have 14 bits on a high gain camera. They typically don't put as high gains in there. So if we look at this, what's the practical effect of this? Again, this is an amplified image for sample here, but if this image was taken with the same camera at low light, so if I look inside this lens here, I can see the center of the lens, I can see all the grayscale variations in the ring out here, and in fact the shiny ring. This was taken by using a longer shutter and lower gain, but now if I turn the gain up and make compensations to the shutter, then this is the same image. Notice the exposure is the same. I can still see the ring. The grayscale values are approximately the same, but you can see how much more noise is in this image, and that comes directly from the gain amplifying the noise in the camera and using a smaller percentage of the well capacity that's available in this particular camera. Exposure time is then the length of time that the sensor is open for collecting the light, also known as the shutter speed or integration time. Exposure time considerations: frame rate may be reduced with increase. So if a camera has a certain frame rate, there's always a certain amount of time it can expose before it can read out and have time. Obviously, if you're looking at a camera that has 30 frames a second and you want to do a 4-second exposure, you're probably not doing a 4-second exposure at 30 a second. Motion blur is greater with an increase in exposure time. Again, we're not freezing the motion, so if I take a longer exposure time, that means an object moving at a fixed velocity through the frame will move further during that longer exposure time, thus causing more blurring. Signal noise ratio is increased with exposure, just as I said, though. So the advantage of exposure is I can keep the gain low and get more light in there, which gives me a higher signal noise ratio, provided I can live with the other two effects above. So paying attention to exposure itself, you'll note the note in here that says good and better are always a matter of opinion and application. So somewhere in here you want to look, if I overexpose the image, I've lost so much information that I probably don't have enough to really make a judgment. Correspondingly, if I underexpose it, I lose it in the black area and there's no recovering that. Whether I clip it black or clip it white, that information can't be gained back. If I have it somewhere in between, then I have information. And if it's not there, I can actually apply digital methods, maybe stretch and get it back. At least it's not clipped away like it is black or white. However, there's optimum, and this is why we're saying it's a matter of opinion. Probably this image gives me the best all-around image here as far as seeing the lens, seeing the ring, seeing the light. But guess what? If there were some kind of variation in the lens, and you can see there actually is, and there's a couple little stripes inside this lens, if I were actually measuring those, I might want to purposely overexpose the image. If I didn't care about inspecting stuff in the exposed area, this might be the kind of exposure I wanted to see, that variation in that black ring inside of this lens. In fact, I can see it best here, even though I said this is probably the worst image here. If I were really concerned with only measuring this variation, I might actually use this image. So be aware. Exposure affects the quality of your image and how far, and the dynamic range. Certainly this is the shortest dynamic range, but if it's also user dependent on what they want to see. So make sure that you're getting the right exposure that's giving you the most grayscale values over the area of the image that you want to use. Black level, sometimes called brightness, though it's almost incorrectly called brightness, adds an offset to the pixel value. So the black level, manufacturers call this different things. It can be called black level, in some cases simply called offset, but this is just a constant we're applying to the image. So it's back to how black is black. In some cases, like if I set a camera up in this room and turned it around and started looking at things like the black frame around this TV, well, there's light coming off. This black frame is black to you and I's eyes, but yet there's a certain number of photons that are still bouncing and hitting it. So the camera will also see that, but in some cases, maybe I wanted that black frame to be black. So the offset gives the user the ability to adjust and say, ignore those few photons that are coming off. This really should be black, and set the right starting point in the image. It does affect the brightness. I don't like this because in the analog TV days, brightness actually affected the white level, the top end of the signal. In the same way you offset the bottom, brightness technically is moving the top level. In the digital camera world, because it's an offset, it's affecting both when I move the offset. But if you're talking to older people that are using analog terminology, they might not like it if you mix black level and brightness. So black level considerations, proper use to ensure camera accurately measures light when the scene is darker. Again, how black is black for the correct point that I'm measuring. And a side effect is that it can make the image brighter or darker, but not by much. So you're mostly affecting the black levels. If I add, say, 5 black counts of offset, and I'm looking at this frame that only had 5 or 10 counts, then I may more than double the output of this frame. Yet when I look in the middle of the image that was starting to saturate in areas where I had 200 counts of light, adding 5 counts to 200 doesn't affect it much. So it will gain the overall brightness by that offset, but it's going to affect the blacks much more than it's going to affect the saturated part of the image. And again, you can see this in this image. Again, what are we inspecting here? If I turn the black level up again, I can change the offset just in this black area, and I can see the starts coming out. It, of course, changed the offset. You can see the center is a little bit brighter here, but just as I was saying, the bright pixels in the center are affected much less than the black pixels in the ring. So again, if I were inspecting this and I were concerned about that ring, setting the black level may be as important, if not much more important, than setting the gain and the exposure. Image format controls the type of image sent from the camera, usually specified by color or monochrome, and then by bit depth. So as we were saying earlier, if we choose a higher bit depth, we have more data to transmit or process. but correspondingly, that gives us more detail than a lower bit depth where we have limited detail. So there's a balancing act between how much transfer and how much processing I want to use versus the amount of detail in my image or the bit depth of my image. Be wary of anyone wishing to view a 12-bit image on a computer monitor. All monitors can display 8 bits or less. So despite the fact that Sharp tells me the contrast ratio is probably about 1,000,000 to 1 on this, it's back to your standards and how they measured that. You're not going to realize that. The same is true in your PC. You can get 12 and 14-bit images displayed in your PC, but Microsoft and most programs are locked in around 8 bits. So you probably used a special program if you were going to view anything more than 8 bits, even on your computer monitor. And even then, the dynamic range of your eyes and your monitor are affected. You have to pay attention to what you're actually seeing versus what the camera or computer vision can see. Certainly, a computer vision system at the computer level, if you're doing math and analysis on an image, can see 1 bit out of 12 bits. It'll do the math and figure it for you. Your eyes certainly can't see 1 out of 12 bits. And many people think they wouldn't need 12 bits, but don't. Again, I see this more and more. Some of the cheapest cameras in the market have the highest bit depths, even though sensors don't warrant it. And you get people, just like in the consumer market, that are shopping by resolution. I want the highest resolution you got. Oh, I want the most bits off the pixel. And most of the time, they're over-specifying their system. So you want to listen carefully on what they need to do, look at what they need to do, and make a balance. More is not better in these cases. It's a balancing act. Can be better if you need it, but if you don't need it, it's damaging to your application. So this again is more or less showing images, but it's also, notice, it's showing the file size associated with this image. So these are all monochrome, but you notice this again is a 1-bit image, so it's all black or white, often called thresholding. To find things, if I want to measure this ring, this is maybe not bad because I can measure the edge very sharp. Despite the glares, but 1-bit image, but only 11 kbits per image that I'm transferring. So if you multiply that times the video rate, 30 a second or something, not very much data. If I take a 4-bit image, now it's going to multiply. I got 4 bits per image. You can see more grayscale and start making out stuff on the lens here. I make the ring out in much greater detail. But I'm now 4 times the data, 44 kbits per image. Again, if there are 30 frames or something, that would multiply up. And if I'm an 8-bit image, I have very good definition in all these, but I'm now the largest. I'm 88K per image times the frame rate of the camera. So these things start affecting the bandwidth and the transfer. Again, you want to get good enough and balance this out with your customer. There's certainly shades in between. Color format considerations. So color cameras used to cost a lot more, especially in the analog days where you had to process that analog signal and do it in the analog realm. There were a lot more components. Today in digital cameras, especially in the machine vision world where the digital cameras are making raw Bayer output, they're as little as $50 more. It's really a difference in the sensor. The camera electronics are basically the same, even though the manufacturer may have to do a little more testing on the color camera. But it's not always something you want. Color images are nice, but they can reduce the resolution. The most common color imagers are Bayer or complementary color imagers, which mean that one pixel is red, green, or blue, and that I borrow from my neighboring to get my color. But that inherently means that I borrow neighboring pixels, and that math called interpolation then causes some errors which limit my image. So in this, if I go read the small black and white print and blow it up at the pixel level with my color camera, I have some color aliasing around the black and white edges. And in fact, one of the points in this slide is to show you that it's a function of color. The amount of aliasing you get and how bad it is, it's actually worse on black and white than it is, say, the yellow and white. So this is back to monochrome is 2D color and color is 3D color. And the amount of error you get to Bayer interpolation is a function of the difference of 2 3D vectors. So this means, again, depending on the contrast and color of what I am, I'll be more or less affected by the Bayer interpolation. Resolution also affects it, much like we're talking about signal noise and bandwidth. More pixels achieve higher detail, but not always better, because more pixels, number one, mean the pixels are smaller for the image format. So if I have a 4 megapixel image or in a half-inch format compared to a 1 megapixel and a half-inch, that means the pixel had to be smaller, which affects everything, signal and dynamic range. Also means it's harder for the lens. The lens has to resolve to smaller pixels, which means I need a higher-end lens. And maybe I didn't always need all these pixels for my application. Maybe I could get it done with fewer. And again, if I don't need them, then you should make this a balancing act, because more resolution means more data to transfer, more data to process. It also means higher resolution means higher price too, because you bought a higher end camera and a bigger imager from somebody. So this comes down to an example, a practical example. What if the customer needs to inspect this box right here, and he's doing a color inspection to check his print and everything is right. He wants to make sure all the logos are correct. He wants to make sure the colors fit the standard, but he also wants to read this barcode. Well, you have to look at the limiting resolution. If we look at just the barcode, this is the barcode at 250 pixels square on the barcode. This is the barcode at 25. So obviously I have no chance to read that barcode at 25 pixels. I had to have something more like 250 pixels in this area of the barcode. But now let's say this barcode is, let's say it's a factor of 6 to the total width of this image. Well, if I had to have 250 pixels across here to cover this much of the image, then that says I probably had to have 3,000 to cover this whole image in the camera. So the two go hand in hand. You have to look at what the minimum object you want to inspect is and what the resolution is, and then carry that resolution over your entire field of view. So in summary, you want to accurately identify whether your application is a low or a high end, and that means everything: signal and noise, resolution, dynamic range. Low-end applications may only need a minimum frame rate and resolution and sampling image to convince and get the job done. Higher-end applications will need deeper data. In the higher-end applications, pay attention to your EMVA reports and stuff on the camera. Select your camera appropriately. Be more familiar with the most common sensors. These are typical Kodak and Sony sensors here. They're available in the market. The ICX285 is probably one of the most sensitive in the market, but the Kodak sensors tend to have larger pixels and higher dynamic range as well, especially in the megapixel. So these trade-offs are out there for you and your customers. Talk to the camera suppliers as well and get recommendations. Don't just buy off of data sheets. Digital cameras are packed with features, many that customers would never think they need. Again, talk to the manufacturer and see what he says he has to get your job done. And don't let bad settings misrepresent the image quality. That wraps up section 2.